haven't set the recording yet. Okay, we are being recorded right now. Thank you for attending the class again. It's not a formal thing. This is going to be the Santa's afternoon show. I'm just kidding. You know how the stand-up comedians will introduce themselves. Yeah, I come from a land far, far away from here. I'm going to close the window. Chem 128A, and today is 2/11/21. Okay, we are talking about, we started talking about hybridization, right? So we talked about hybridization going into bonds. So that's leading to the bonds happening, chemical bonds. Okay, so that's where we were. So we talked about this business. Hydrogen 1s1, that's hydrogen, right? That's it. And this is carbon, ground state. 1s2, 2s2, and 2p2. Okay, see how I raise it a little bit. This level, there is a level gap, right? That means 2s is higher energy than 1s. 2s is more energy. 2p is greater energy than 2s. Okay, there is a difference. You don't really have to do that when you just write it out. Like when you do this, 1s2, 2s2, 2p2, you don't have to raise it. It can be at the same level. But when you do that, when I draw the box representing each orbital, then I tend to draw it a little bit higher. You don't really have to do it. Okay, now this guy goes to the excited state, and then I'm not going to worry about the 1s orbital because that's the core orbital. Then this happens. Okay, 2s and 2p. But if that were the case, then the bonds would be, we already talked about it, this would lead to a methane molecule that looks like this. Because s orbital is smaller, s orbital is smaller, 2s, and these are the p orbitals. Okay, px, py, and pz. Okay, so that's made from 2s orbital. This is made from 2px orbital. Let's say this is made from 2py and 2pz. And these are hydrogen's 1s orbital. So if that's the case, this is how the methane molecule should look like, with 3 long bonds and 1 short bond. But we know that that's not the case. Okay, in real life, the molecule has identical bonds. This is expected from here, from what we learned up to that point. This is from results. Okay, this is data driven. This is how it was found in real life. All the bonds are same. Therefore, we suggested that it undergoes sp3 hybridization Essentially, it means mixing. That's it. Simple. 1 part S, 3 parts P, and you get 4 identical orbitals. And these 4 identical orbitals are sp3 hybrid orbitals. Okay, now it binds with 4 hydrogens. They come with, each comes with 1 electron from the 1s orbital, right? You know what? Let me just draw it in blue. 4 hydrogens, hydrogen, 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 and hydrogen. They all come with one s orbitals. So now at this point, you have a CH4 molecule. This is where we are talking about a CH4 molecule with 4 identical bonds. Let me just change the color to blue. Okay. Okay, and this is a CH bond. It's not just a hybrid orbital, but it's actually a CH bond because it's going to have both electrons. This is a CH bond, another CH bond, another CH bond, another CH bond. How does the CH bond look like? This is the hybrid electron in the sp3 orbital from carbon, and this is the electron from hydrogen. So each is a CH bond. Okay, so this is, if I can just elaborate a little bit more, if we could see the color change. Okay, so this electron is there, and this electron is there. That's the CH bond. I'm going to take a pause for like 15 seconds, make sure that you guys are following it. Hybridization, we are kind of reviewing what we discussed. We're gonna start talking about the shape of the molecule pretty soon. Okay, so each bond is this electron and that electron. If we had drawn the Lewis dot structure, the Lewis dot structure would look like this. I'm just going to make some shape, like a little long. Okay. So that's the CH bond. This electron is sp3 hybrid orbital electron, and that electron is 1s electron. Okay, now I'm going to pause for 15 seconds one more time. Make sure you are following everything so far. I'm going to take a snapshot and erase the board and start talking about the shape of the molecule. I'm going to, excuse me, I'm going to stand right in front of the camera. Sorry. There you go. All good? Any questions? Don't put anything in the chat. I'm too far from the screen. All right, so ground state, excited state, and hybridized state, no difference in energy level, identical shape, identical energy, identical property of this electron. And then when you make the bond with 4 hydrogens, this is what it looks like. In pictorial view, 4 same length bonds, same, everything same, okay? Let's erase the board. I'm going to erase pretty much everything that we have here. Okay. So now we have to talk about, we have to discuss, like, what does the methane molecule look like in real life? So our target learning outcome should be shape of a molecule. Shape of a molecule, okay? Now, this molecule, methane, you know what? It will be easier if I just draw the bonds in blue, because I have some model, then it'll be more easy to see for you guys to see. I'm going to draw the carbon in black. Blue, 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 and blue hydrogen. Okay. Realize one thing, that each bond is made out of 2 electrons, right? A black electron from carbon and a blue electron from hydrogen. You know, in real life, they're not black and blue, but then this is for our better understanding. Okay. So realize that each dot represents an electron. Okay. These are electrons and they are negatively charged. What happens when you bring 2 protons close to each other or 2 cations close to each other? Should the same charge attract themselves or repel themselves? What do you guys think? Speak up, please. Don't.
They repel themselves?
They will repel, right? This is negative and negative. They have a bond. There is a reason for them to be together. That there is nothing wrong with that. But imagine that this highly negative charge density here, 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 and here, it's almost like sticking 4 bar magnets. I'm sure you guys have seen bar magnets. These days, everything is like disc magnets or something. And if you're playing with it or you're using it like a little sticky thing to post your greeting card or birthday card or some card on your refrigerator, so put some pictures, right? You have disc magnets. But if you could take a bar magnet, one end is north and one end is south, and they line up with south and north pole of our Earth, right, of our planet. So just imagine, I'm just playing with my models. Imagine if you could put 4 bar magnets, okay, with their north poles, the north ends stuck together. If you could force them with some kind of a flexible connector that will allow the magnets to kind of move around, okay? The question is, the north poles would repel each other and the south poles would repel each other. So what kind of geometric shape would that adopt if you could put 4 bar magnets? I bet somebody has thought about it and there are probably toys like that. Does anybody know, has Anyone in the audience ever played with magnets with some kind of an attachment at the end, so that you can see like what happens when you put 2-bar magnets, what happens when you see put 3-bar magnets, what shape do they take, and what happens when you put 4-bar magnets, with the same poles at the same end, what shape do they adopt? Does anybody know of any toy such what I'm describing? Anyone aware of anything? We can Google later on, but I don't want to waste time right now. Anybody? No? No idea? Okay. So that's fine. So if you could put that together, okay, this is definitely the methane molecule with the 4 carbon hydrogen bonds, right? 4 carbon hydrogen bonds. They are not going to look like a pyramid, okay? Because their whole idea, their entire idea is to stay away from each other as far as possible. I'm sure there is a better way you can organize 4 sticks connected to the center in a way so that they are farthest away from each other. That's the whole idea. That's the shape that the bar magnet contraption would adopt, three-dimensional shape, to basically be farthest away from each other. That's the happiest shape, right? So when you do that, the shape, well, I don't want to cut through this drama. Okay, I want to make sure that I think most of you know what I'm talking about. The shape that this molecule is going to adopt is not flat, is not like a pyramid, square pyramid. It's going to be what? It's a T word. Who remembers? What shape does it adopt?
Tetrahedral.
Tetrahedron. So the noun is tetrahedron and the adjective is tetrahedral. You could say, I am tetrahedral because I look like a tetrahedron. Okay. So now tetrahedron, O-N is the noun. Okay. And the best way to describe what a tetrahedron is the following. I learned it in an Indian chemistry textbook, and I have never seen it in any other textbooks that are followed in this country. I may have missed it. I'm not a very good textbook reader also. I skip pages and stuff. So let me show you like what a tetrahedron looks like. You can probably appreciate it better. Okay. So the shape of this molecule, shape of this molecule, you already know, is tetra excuse me, hedron. What is a tetrahedron? You can say, yeah, like this, like that, one up and one down and one wedge and one, let's get to the bottom of it. I want to draw a big cube. I'm using a lighter color so that the cube doesn't come in our visionary path. Okay. This is a cube. All right. Put the carbon in the center. Put 2 hydrogens on the top surface of the cube across, either here and here or here and here. Let's put them here. I'm just going to put a circle here. Okay. Put the 3rd and 4th hydrogen down on the bottom surface across that line. Okay. If they're here and here, put these 2 guys across so that the line joining them is perpendicular. The top is like this and the bottom is like that. Okay. Now join the dots. It's that simple. This one coming from the middle to this edge, if you think about it, if you can imagine, I don't really have a cubicle anything here in my office. There's a coffee pot. No, it's not going to help. It's going to make things more complex. This bond is coming toward you. So as you see things far away, it looks tiny, right? as it comes closer to you, it kind of widens out, right? Like a wedge. So we use a wedge to show or to basically send the message that that thing is basically sticking out toward you, okay? So this bond is going to be drawn with a wedge. Okay, that means it's out toward you. This bond, on the other hand, is going to be drawn with a dashed line, kind of widening as it goes further back from the center. So this molecule, if I just draw it outside, blue, sorry. Looks like this. So that's a true representation of methane molecule in 3D. Okay, this is 2D, two-dimensional representation. This is 3D. Okay, this is three-dimensional. Now, the more the convention of representing a methane molecule or an sp3 element is not exactly like that. There's nothing wrong with this, but the real representation, I'll show you what it looks like. Let me make a model of it. This is the time when you should seriously consider purchasing or not purchasing a molecular model set. Okay, so the way I have drawn this molecule is kind of like this. Okay, the two top bonds are on the whiteboard. If this is the whiteboard, this is my best whiteboard representation. That's the whiteboard. These two are on the whiteboard. This is the wedge coming toward you, and that's the dashed line going away from you. Okay, you better get used to the three-dimensional representation of molecules. Okay, buy a model. This is the right time. You are the best judge of your understanding and your capability. Buy a model set if you think that it's going to help you. This is perfectly fine. The convention is, this is the convention. The convention is to do it in a slightly different way. Okay, if I can fit them here. So you have your carbon here. The convention is you draw one line up vertically and a solid line, that means it's on the whiteboard, kind of an angle. I don't know what the angle is. It's not 45. Let's say it's 30 degrees. Okay, here, the wedge and the dashed lines are drawn this way. So how are we holding on to the molecule? Kind of like this. Sorry, kind of like this. One bond is up, the solid line that's on the whiteboard. That's on the whiteboard. This is slightly angled, not perfect, not horizontal, slightly slanted. That's down. This is vertical. This is slanted. That's the wedge. And that's the dashed line. Okay. It doesn't matter how you draw the molecule. You can draw it anyway. But remember that drawing it in different ways doesn't really make the molecule different. Okay, I'll try to pause and make sure that you guys understand. What I'll try to do is I'll try to see if I can keep the chair here. Can you guys see the model? Kind of see the model, right? Yeah, so let me just pause for like a few seconds. Make sure you understand the shape of tetrahedral and how to draw it. Get used to drawing it. Start drawing the three-dimensional representation of methane. Okay, when you have an sp3 carbon and you have 4 bonds coming out of it, this is exactly how it looks like. Okay, I'll keep the chair on the left side so that it's still in your periphery. And let's talk about some of the properties. Of course, each bond is identical, same length, same every other property. And the angle, all the angles for a tetrahedral. So this is tetrahedral. Tetrahedral. What's the angle? Who remembers from the past? What's the angle? Is it, let me throw some numbers. Is it 45? Is it 90? Is it 109.5? Is it 120? Or is it 180? Which one is correct? A, B, C, D, E.
C.
Yep, the angle is, you're correct, 109.5 degrees. You can actually calculate it. This is just very simple geometry. If you're pretty good in geometry, you can just draw it out and you can figure it out. It's probably, if I try hard, I can probably figure out why this angle should be 109.5 degrees. It's actually 109 degrees and how many minutes? Who remembers? 109 degrees and 58 minutes? I forgot the exact number. Who remembers? Anybody remembers? No? No memories from the past? Vincent, Hardeep? Remember the numbers? No? 100, how can it? 28 minutes. What is wrong with me? 109 degrees and 28 minutes. So 30 minutes is 60 minutes is a degree. So it's almost like 0.5, but by short by 2 minutes. 109 degrees and 28 minutes. All right. That's that. Okay. So let me take a picture. And are you guys comfortable with the shape of tetrahedral, tetrahedron, shape of anything that's sp3?
Yep.
You're reasonably comfortable so far? Okay. So the bottom line is, whenever you see an element in sp3 hybridization, its shape will be approximately kind of tetrahedral or tetrahedral-ish. That's bad English. Tetrahedral-like, or sometimes we say distorted tetrahedral. So like this element, like we have so far what we have discussed is, we have discussed methane, a molecule between hydrogen and carbon, and we have described hybridization. Let's take it to the next level. Okay, let's check out a few other elements and compare them with methane. Something like a small molecule made between two hydrogens. Hydrogen and carbon we have already discussed. Let's discuss a molecule between hydrogen and boron, hydrogen and nitrogen, hydrogen and oxygen, hydrogen and fluorine. Let's go through those. Maybe I'll make some columns and keep the methane in first column and do the rest of the molecules, and then it'll probably become a better idea. I'm going to zoom through it very fast. I expect you to kind of follow me in a rapid manner. Okay, so this is going to be fast demonstration of few other elements, and they're bonding with hydrogen. So let's do that right now. So carbon, nitrogen, oxygen, and fluorine. Let's make 4 columns. Okay, we are still talking about hybridization. I'm not going to block the board. We're talking about hybridization, making molecule through making bonds. Okay, so let's make some columns. 2 halves and 4 quarters. Okay, let's put hydrogen on the top. It's 1s1. Hydrogen 1s1. Hydrogen should probably write it's 1s, not 2s. Okay, first one, carbon. I'm just going to start with the valence shell, not worry about, you know what, let's draw the excited state. Get used to that. That means excited state. 2s and 2p. Then it undergoes sp3 hybridization. Okay, sp3, 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 and sp3. Then it makes the molecule. It forms CH4 molecule. And that time it looks like this. This is the actual CH bond in a CH4 molecule. Okay, it uses an electron from carbon and it uses an electron from each hydrogen. Okay, so this is a CH bond. This is exactly how the CH bond looks like. And the molecule looks like this eventually. Tetrahedral, a perfect tetrahedron. Each angle is 109.5 degrees. What we just did. Let's move to nitrogen. Let's make a molecule between, so this guy is CH4. The molecule we're talking about is CH4, methane, the smallest hydrocarbon. Okay, now let's move to nitrogen from carbon. What does nitrogen look like? Only valence shell. We don't care about the core shell, so don't get confused. Valence shell, 2s2, 2p3. We don't really have to make it excited state because they're already kind of there. Okay, when it makes a molecule, so you tell me, we have already gone through it before. What should be the formula of the smallest molecule? Smallest molecule made with 1 nitrogen and few hydrogens. What's the formula? NH, NH2, NH3, NH4, or NH5? What's the correct answer? How many hydrogens should combine with 1 nitrogen?
3.
Why, if I ask you to explain why 3? Because 3 unpaired electrons, right? Okay, sounds good. It has been found that even though there are 3 single electrons, from the property of the NH bond, it has been found that it's not just pure p orbital. It has been found that when you actually see the nitrogen hydrogen bond with a lone pair, Okay. It has been found that the property of the bond is in between S and P. Okay. It's not just P. Not P is, are you asking why? That's fine, totally fine. What was it, something someone asked? Can you repeat? Or it was something that was not meant for me? You can say that yes, I was asking you why. Okay. I'll give you the why answer. The why answer is it's result oriented. Okay. Because when the ammonia molecule is analyzed and its bonds are examined, it has been found that it has the properties of P and S both. So the length of the NH bond is not as short as would have been with just S, not as just as long as it would have been if it were just P. The length of the NH bond is in between the size of S orbital and P orbital. So where I'm going is, I'm going to this conclusion. It also undergoes sp3 hybridization and makes, take it with a pinch of salt. It's going to be almost identical energy, but you realize that one of the hybrid orbitals, pretty much at the same energy level, will have a pair, that guy. And these are going to be the single electrons in the sp3, 3 of the 4 sp3 hybrid orbitals. Then NH3 happens. Then it binds with 3 hydrogens, and NH3 happens. As NH3 happens, how does that look like? There is nothing here. This is just a lone pair. This is just a lone pair. The next one, an NH bond, an NH bond, and an NH bond. Okay. In real molecule, a pair of electrons, one electron from here, sp3 hybridized orbital, and the hydrogen's electron upside down. This is the NH bond. This is the NH bond. Okay. So this electron is that electron, and this electron is that electron, and that same goes with the 2 other bonds. Again, the shape of the molecule will be sort of a tetrahedral, but not a perfect tetrahedral. So you have to draw something here, wrong, a wedge, and a dashed line. What am I going to do is I'm going to make it simple for you. I'll put the lone pair up here. Like a little ghost, friendly ghost. Hydrogen, hydrogen, and hydrogen. You can either call it not a perfect tetrahedron, but you can call it a distorted tetrahedron. Okay, I'm going to write it down in black so that it stands out. You can call it distorted tetrahedron, or you can call it something else. If you ignore the lone pair, what does it look like? You see them in a place called, in a country called Egypt, in the middle of the desert.
Pyramid?
Pyramid. What kind of pyramid? Is it three-pointed triangle, or it's got a name? It's called, anybody remembers? Something pyramid.
Trigonal. Oh,
Trigonal pyramid. There you go. Trigonal pyramid. This is also called trigonal pyramid. That's how the molecule between hydrogen and nitrogen look like. Now let's go to our famous molecule on our planet, water. Okay, oxygen. 2s2. Pair. Oops, wrong. 2s2 to p4. Undergoes, the molecule will look like this. Okay. And it'll undergo sp3. Oops, wrong color. I've become really fanatic about maintaining proper colors. sp3, 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 sp3. Two of them are pairs, not really useful for making a brand new bond. Single, single. So it's bivalent. It can make two bonds with two other guys to share electrons. That's what it looks like. Now, in real water molecule, when you actually have the water molecule made, this is what it looks like. This is actually the oxygen-hydrogen bond. And this is nothing but a lone pair. Lone pair, for the time being, it's useless, but it can be very useful. You will see later on. Okay? That's the OH2 bond. And if we just draw the molecule, let me just draw the molecule in a slightly different way, kind of upside down. Let this be the wedge, and let this be the one in the back, and let this be on the whiteboard. So I'm just using a different convention to draw the molecule. So sorry. Okay. So I'm just holding the molecule this way. The two bonds down here are on the whiteboard, and the one lone pair is out and one lone pair is in behind the whiteboard. Okay. So that's kind of like our wedge, because I darkened it. Just forgive my compromised picture. So this electron again is that electron. I screwed up. This electron is that electron. It's going to be very difficult otherwise to route it to the right bond. That's that electron. And same is true for that bond. And that's one lone pair. This is another lone pair. Okay. The shape of the molecule. One more time. You can call it distorted tetrahedral. You can cheat. Distorted tetrahedral, or if you ignore the lone pairs, what shape does it come to your mind?
Band.
Bent, or what English letter is this?
V.
You can call it bent, or even you can call it V-shaped. If you forget, write distorted tetrahedral. If you cannot remember distorted tetrahedral, you can say, I don't know, Come up with a word that means distorted. And or you can say bent or V. Don't say linear, that's bad. Okay. So methane, carbon and hydrogen molecule, ammonia, nitrogen and hydrogen molecule, oxygen and hydrogen molecule. And let this be your homework. Let this be your extra homework. How do you figure out fluorine? It's identical, same principle. Why don't you practice it? 2s and 2p, not right now. Figure out the rest. And then finally shape. Okay? Hybridization, shape, and everything. Let this be your homework. Extra homework. Later on, through the weekend, because it might be important for the quiz. Okay? I'll take a snapshot of the board and take a little break. Let you guys absorb everything. Sorry, I'm blocking the camera. Any questions? These are all very important stuff, okay? I am debating between continuing with more hybridization or using this knowledge so far that we have gained and stick with sp3 for the time being and start discussing alkanes. I know that you guys are probably not mentally prepared, or those of you who like to study ahead of class. I know somebody actually, I forget which class, mentioned that can you just let us know ahead of time like what exactly we are going to be discussing in the next class so that I'm more prepared. That's very commendable. I really appreciate it. And I'm ashamed to say that I haven't done that. But I know that you're not prepared, but I'm thinking about starting some discussions on alkanes right now. Take a break from hybridization, because in the past, I would talk about sp2 and sp hybridization, and I think it's too much hybridization talk. If we take a little break, it'll probably do more good to your health and mental health, all our mental health. I think it'll probably fly better. Let's take a break. Let's talk about alkanes. Let's talk about cycloalkanes. And then we will eventually, when we discuss alkenes, we'll talk about sp2 hybridization. By the time you will already remember, learn, forced to learn, be examined, tested. So I think it'll be in your system. So learning sp2 and sp should not be a big deal. If I teach everything now, it'll probably be subliming into the atmosphere more. Okay, that's my opinion. If you want to learn more about sp2 and sp right now, you guys can vote. I'm open at this point. But I think we have had a lot of Born and electronic configuration and blah, blah, blah for the time being, for quite some time. Okay. 15 more seconds of break, and then we can go from there.
Professor, I had a real quick question about our upcoming quiz.
Yes. Why not we do the following? I'm not cutting you off, George. Cassandra. Cassandra, just give me a second. We'll wipe off the board, and then let's have a 5-minute discussion on the quiz. Okay.
Okay, sounds good.
And then I'll get back to you, Cassandra. This is okay. This is fine. This is still kind of old material, but then I know that sometimes hybridization can freak you out and get upside down in your system. Okay. But I think it's better to talk about alkanes and continue with this discussion. I took a picture. Yeah, I did. Sometimes I can. Okay, so we are now talking about, I'm not going to take a picture of it, but it's going to be in, in the video. So Cassandra, maybe I'll let you ask, or anybody else ask, if you have any specific questions about the quiz.
It was kind of just a general question. I know for quiz 1, we're supposed to focus on chapters 1 through 3, but during the lectures, we're kind of focusing on chapter 1 mostly. So I'm wondering if you want us to just book base the other 2 chapters.
Okay. My exams and quizzes, whatever we have discussed in the class, that's what is going to be in the quiz or in the exam. Okay. If you haven't seen it in the class, in the lecture, it's not going to be in the quiz. Does it answer your question?
Yes, perfectly.
Anything else? I haven't decided if it's going to be a hybrid, yeah, S and P. It's going to be hybrid between Canvas, multiple choice exam, quiz, plus maybe 1 or 2 free response questions. I haven't decided that yet. It could be fully free response, and you'll have to write it down and upload it the way you did it for practice exam, or it could be a mixture. Okay, it's not going to be 100% Canvas multiple choice. I hate to have this discussion, but since we're discussing it, I'll just mention it. When you do the multiple choice questions, work alone, open book, open web, open resources, everything is open. Okay, anything you can check anything you want. But realize that if you don't study, if you're not prepared, if you're scrambling through resources, it'll probably not be a good thing for you to do well. Okay. When you are taking, you should work alone. You should not discuss it with fellow students or anybody else. Okay, any other senior student or somebody else. Okay, I'm trusting you, so you should reciprocate the same way. The free response question, I'll make sure that I see your signature in there. That means it'll be something that you will have to really come up with. Okay. If there is something funny going on, you know what I mean by funny. If anybody has consulted and copied or something like that, if I sense that, it's going to also affect your Canvas multiple choice quiz, because I'm going to take off, if I see something that's obvious, I'm going to take points off of your multiple choice question too. So let's say there is 15 points from the multiple choice quiz. I haven't decided yet. Let's say if we're doing hybrid way, 15 points for the multiple choice and 5 points for your free response. And the free response is definitely sketchy situation, right? 2 people, 1 person has copied from the other. Whether I have let my friend copy from me, I don't care. I'm going to give both of you 0 out of 5, and I'll probably take off some points from your, even if you got 15 out of 15, I'll take off maybe some points from there. I don't know, 3, 4, 5 points from there, equivalent of the free response. So I'm not trying to be sound mean or anything. I'm just trying to reduce cheating. That's it. Because, you guys know that virtual learning, virtual teaching also, enables teaching, cheating quite a bit. So that's that. So just think twice before you do anything funny. I don't think that's going to be the case. I think I trust you, and it should be a clean exam. Okay. Any other questions? Sample question could be, 1 as to which element. Is it boron? Is it carbon? Is it fluorine? Or is it lithium? A, B, C, and D. What's the right answer? If it is a multiple choice question, it could be something like that. What's the right answer?
Fluorine.
Okay. C. Another multiple choice question could be nucleus. Look at the element. What is the atomic number for this element? How do you calculate?
9. There's 9 protons.
Okay, one answer is 9. Anybody else wants to prove her wrong? Who or shoo or cheer or jeer, or anybody wants to throw like virtual paper balls at her through the camera? Agree or disagree? Come on, guys, say something. It sounds like a first line.
I agree.
I agree.
I
agree.
Okay. If I ask you to represent this species using, the letter codes and other things, what would this be? What is it? What is it? Chicken or monkey or goat? Goat on a tree?
Fluorine.
How do I say it? What's the code for fluorine?
F.
Correct answer?
Would it have a positive charge?
0 out of 3.
Positive charge. Negative charge.
Figure out why those are wrong answers and why F minus is the right answer. Figure it out. Let's do another simple one, something very similar. Nucleus. What is it? Think before you answer. Give me the correct answer. What is it?
Lithium negative charge, or positive charge, sorry, positive.
Is everybody following? I know some of you like to not answer.
Yes.
Yes.
Okay. When the semester ends and when it comes to the final grading, I will not forget about that 2 bonus points, and I'm going to go to some random videos from Canvas, and I'll see who has their cameras on and don't have the cameras on. I'm not asking you to turn on your cameras on because I understand that there can be an inconvenience and many other reasons to not to do that. But don't forget about the 2 points. Okay. That's the kind of questions you might be seeing. Okay. So let's talk about what else can we talk about between lithium plus and fluorine minus. Okay, which of the 2 ions does not have a core shell? That and that. Which ion does not have a core shell?
Lithium.
Sounds good. All right, let's talk about something different. Let's take a break. I'm tired of electronic configuration and Lewis dot structure and everything else. Well, Lewis dot structure of, let's do one more. If we're doing Lewis dot structure of these ions, this guy and this guy, how do we do it? Lewis dot structure of lithium plus. Okay. Let's do just simple lithium. How do we draw the Lewis dot structure of lithium?
1 electron.
One, okay, uppercase L, small I, and lithium. What about the lithium ion? What do I put? Lithium electrons, any electrons or no electrons? What do you do?
2 electrons.
No. That's something that bothered me for a long time when I was a student. You don't show what used to be the core shell. It's important that even though this guy doesn't have a core shell, but this used to be its core shell, we don't show the electron because then it gets very complicated. Then that becomes its valence shell, but which used to be not the valence shell for neutral lithium. So we don't show these electrons. We just say nothing. Because you want to send the message that lithium lost the electron that used to be on its valence shell and now it's gone to make lithium plus. So that's important because if you put 2 electrons, it's going to confuse the hell out of many people. Okay, that's just not the convention. If you're wondering, like, why not? I want to put those electrons because that's what is on the outermost shell. That's its valence shell. I agree, but that's just not the convention. We can argue about it. Okay, so that's lithium ion. So we learned something, what not to do. Fluorine. Fluorine minus. How do we show its Lewis dot structure? How many electrons around it?
I'm guessing.
7.
7. This guy, okay? If you do F minus for that, you get 0 out of 3.
No,
That's not F minus, that's F. That's neutral F. So what's the problem? So this is wrong.
just have one more.
Wherever it snaps from, It's got one more. It probably belonged to the lithium. It probably snatched it from the lithium. So that's correct. This is F minus. Make sense? I'll give you guys a little break. I think we will catch up again on Tuesday. Monday is a holiday, I think, whatever day that is, President's Day. And we will talk about alkanes. Okay, there you go. We will talk about alkanes followed by cycloalkanes from Tuesday onwards. We'll have the quiz at the end of the class on Tuesday, and then we'll go from there. Okay, have a great weekend, guys. I'm not taking a picture of this board. I'm just letting you guys go because I always take extra time. So today I'll compensate for that. Have a good weekend, everyone. Bye.
Thank you, Professor. You too.
Bye.
Thank you, Professor.
Bye-bye. Thank you.
Be safe. It's going to be over soon. I think things are getting better. Take care, everyone.